Okay, so I have a ramp and I have a vertical loop. There we go. 13. Thank you, John. I have state A right here, which is located at a vertical height L. This is a vertical loop that you can, go around and around. So the trajectory goes start at A, it goes here, and then that's what's happening. So they've given us a couple of points. First, they've given us the radius, R. So L is given, R is given, and they're going to call this point, and this point. Let's do those three. You can do the rest, which is the other one opposite to C, D, and B. Okay. So we have a system that starts at A with a particular given mass. It's released from rest. So that tells us something about the kinetic energy if we want to pick that position. And it slides down the frictionless ramp before sliding horizontally towards point B. And then it goes through C and D. Okay. You know what? Let's add a little bit of fun and put friction on the distance D. So let's imagine D is given, and there will be friction only on the horizontal area. So not on the ramp, but as it slides horizontally. And what they're asking us is they're asking us the velocity and the normal forces at those 3 points. Okay. Before we start, what is it that we should notice? Is there any particular shape that our system is going along that we've seen before that is of interest? It's going through a ramp, okay? It's going through a horizontal surface, okay? What is it that it has to go through B, C, and D? How do we call this? Yeah, vertical loop, therefore a circle. Excellent. Circle means circular motion. What do we know about circular motion? Right away. A is equal to V squared over R. And there is always a component of the acceleration, which is AR, which is towards the center. Good. Maybe we're going to have to use that. Perfect. So let's start with point B. Let's figure out the velocity at B and the normal force at B. So obviously that is going to be our second point that we're going to consider in the energy conservation law. First point that most likely we want to consider is point A, because we know its height, therefore we know something about its potential energy. We know its velocity, it's at rest, so we know a lot of information in there. So let's pick A. So let's write down the energy conservation law. The only system that we consider is the object that slides, therefore we have an energy term for each. We do not have any spring, so we can just get rid of it to save time and space. So we only have the sum of the work term plus KE plus PEG. We can ignore PES again because no spring. KE plus PEG. This is going to be at point B, and this is going to be at point A. All right. As the system goes from A to B, can you do a quick free body diagram, say at point F? What are the forces acting on our little object at point F? Excellent. The weight as usual, first one. The second one is the normal force. All right. And friction, because I just added up. So it's a variation of 13, which obviously is Fk. Excellent, Tyson, because we're moving. Since we're moving towards the right, property of the friction is to go opposite. Excellent. Therefore, it's going to go towards the left. Good. Cool. So that means we have three work terms to consider. Let's go down the list. Again, the first one is the weight. We don't have to calculate and include the work done due to the weight because we have chosen to include PEG instead. No worries. Let's look at the work done by the normal force. Anywhere between A and B, or every time your system slides on a surface, the vector n, which is the normal force, is always perpendicular to the displacement, whether it's on the ramp or the horizontal surfaces. So again, every time your system slides on a surface, the normal force is always perpendicular to the displacement, and hence, as we calculate the work due to the normal force and investigate the dot product, we have a natural and easy, nice little zero. So really, out of those three forces, we have to consider one, friction. No problem. Let's calculate the work done by friction. By definition, Fk dot dr, and we're going to go from 0 to d. What are we going to pick up naturally as we're going to do the dot product, which is always true when you calculate the work done by friction? Due to the property of friction with respect to displacement? Yeah, excellent. Fk stirs the left, dr stirs the right, therefore naturally, due to the property of the dot product, we pick up the usual negative sign. And now everything is scalar, we can integrate. Fk is mu kn, it's a constant, we can take it out. And now this integration is trivial. And we have this, same as last Wednesday. The problem is we still don't know what n is. So we have to express the normal force in terms of known quantity only. Let's go back to our free body diagram and try to figure out which clever coordinate system that I could use in order to express the normal force in terms of something that I know entirely and that doesn't include other quantities that I may not know. In this case, trivially, we can pick one of the axes along n, the other one perpendicular to it. And as we apply Newton's law in the y direction, we realize that the acceleration is 0, and therefore we end up with n negative mg is equal to 0. Hence, in this particular case, the normal force is just the weight. Perfect. Now we can substitute this in the work term, and we have negative mu k mg times d. Now, this work term is entirely in terms of known quantity. You can just plug numbers and get a value if you wanted to. Perfect. So let's go back to our energy conservation law equation 1. Let's substitute the work term. We're going to have negative mu k mgd, the kinetic, 1/2 mva squared, the potential, mgha, and then the kinetic on the other side, vp squared plus mghb. All right, now let's go through each of those remaining energy terms and ask ourselves whether they're 0 or not. First kinetic term at A. For us to identify whether we need to keep it or not is to ask ourselves the question, is our object moving in state A? If the answer is yes, we keep it. If the answer is no, as Tyson confirms, and on lookout, we nuke it. Just like on TV. Flip it or whatever. HA. Well, I've been sloppy and I forgot to do something. But it's okay. I realized that I forgot to do it as I'm going through the term of PEG. I obviously need a coordinate system for me to express the functional form of all my potential energy due to gravity. Where would you like to put your data? Would you like to, or your x-axis? Would you like to pick it at A? Would you like to pick it at F, at B, at C, or at D? Excellent choice, Sonoka. So that's another case where, to make our life easier, if we pick F or B, doesn't matter, right? Life will be easy. So I strongly suggest, again, that you redo this problem by picking it at A, then at C, then at D, and then you're going to realize, oh, okay, yeah, that's going to be a pain in the ass. So let's pick it at F or B. Remember, when you do energy, the Y has to be vertical and positive up, and the X can be anywhere. So I'm going to start measuring all my h's from this. All right. So now can we answer the next question? Is our object at state A on our x-axis? If the answer is yes, we nuke it. If the answer is no, we keep it. No, excellent. Next question, let's try to figure out HA. Is state A above my x-axis or below my x-axis? Above. Thank you. Therefore, we know it's going to be positive. Do we know the vertical point or value of state A? Yeah, excellent. MGL. Perfect. So this term becomes mg positive L. Good. Next, obviously we have motion at state B because that's what we're looking for. Therefore, we keep that term. What about HB? When we are at state B, are we located on the x-axis or not? Yep, we are. Therefore, we nuke it. And that's it. Now we can solve for VB. M is everywhere. And we can solve for VB, which is going to be G is common, so we can take it out. And that's it. L minus mu KD. Then we multiply by the factor of 2, and then we're going to take the square root, and we're only going to keep the positive value. All right. Perfect. That's the velocity at point B. Any questions so far? Everything okay? So keep in mind, always associate energy with velocity. Every time the problem asking you to calculate the velocity, always think energy. Sure, you could use Newton. But if you use Newton, first you have to do a whole Newton analysis, but Newton will only give you acceleration. Then you have to add kinematics. That sounds like a lot of work. Rather, you could bypass those two different methods by just doing energy one line. Perfect. Now the next question is calculate the normal force at point B. So if now we're interested in identifying the magnitude of a force, what would be the best method to use? Energy, kinematics, or Newton's law if we're after a force? Yeah, obviously Newton. Newton is all about forces and acceleration. Kinematic is all about kinematic variable, acceleration, velocity, displacement. Energy involves usually velocity and position. So let's do a free body diagram at point B. This is going to be obviously very similar than point F. The only difference is we have the weight, we have the normal force, and that's it. We just left the period distance d where we had friction. So really only two forces. But this is the trick to this problem. At the instant of B, this is the instant at which we start going into a circle. Therefore, we know that at the instant at which we start going through the vertical loop, therefore at which we're at point B, we are going in a circle. Therefore, we do have an acceleration, which is always directed to the center, and therefore is entirely up at point B. Hence, as we apply Newton's second law, and let's pick the same coordinate system. You can pick a different coordinate system if you wanted to, but again, since we know that at point B we start going in a circle, therefore circle tells us, A is equal to v squared over r, and A is towards the center. Then let's pick one of our two axes in the same direction as the acceleration, which allows us to write that the sum of the forces in the y direction is going to be N minus mg is equal to MAR, the radial. Okay? And we know, since we're going in a circle, that this acceleration AR is related to the tangential acceleration that we just obtained. Let's substitute it in there. Bing! And now we can solve for n. As we substitute the functional form of VB, we're going to have m over r times 2g L minus UKD. And therefore, n is equal to mg. We can factor both of those buggers. 1 plus 2 over r L minus UKD. Okay, so obviously, as we start going in a circle, the normal force is not just the weight, like it was on the horizontal surface. It's going to pick up some magnitude by this much. Okay? So that was the trick here. When you deal with a circular loop, you identify the instant at which you start going in a loop. And at this case, remember that every time you go in a loop, not only you have a radial acceleration, whose direction is always towards the center, but you also know that its magnitude is related to the tangential velocity at that particular point. All right. So questions for champions. If now we are, let me duplicate all this. Let's redo the same problem at point C. This becomes C. Obviously, the work done by friction is exactly the same. So let's see which terms are going to be different. So this part doesn't change, negative mu k mgd. Obviously, everything we wrote here got to be the same. So we had this. That doesn't change, right? 0 plus mgla, or L. Now the new thing is this. Now instead of doing B, we're doing C. So obviously we still have kinetic at point C, because now we're looking for Vc and N at C. Therefore, we're going to have 1/2 mvc squared. And then, and I get back to you, Ray. Let me finish last term. Excellent question. What would be the new potential energy at point C? Same question. At point C, are we on the x-axis or not? Nope, assuming that we choose the same one at F. Therefore, we have to keep it. Obviously, point C is above, therefore we expect it to be positive. By how much is it going to be above? That is, what is the vertical position of point C as measured from the x-axis? And remember that the vertical loop is a circle. Yeah, thank you, Tyson. Excellent. MGR. Bing, that's it. Now, Ray suggested, hey, why don't we start with B? We could have been. We could have done the exact same thing and do it between B and C. Absolutely. The advantage of doing it from A is that if we had goof anywhere here at VB, then the next problem will be wrong, because we will have to rely on the kinetic energy at position B, which would need this. So if we're 100% confident we did this right, sure, we could have picked the point B and C. If we want to stay on the safe side, then as we pick A and C, it doesn't involve anything about B. Therefore, we could have goofed in the first part of the problem and still got the second part correctly. So it's totally up to you. Excellent question, Ray. I would strongly suggest that you redo this problem between B and C and see how things changes. But you should get the exact same answer. Good, 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 good. So here we're looking for C. So let's solve for C or VC. G is not everywhere, so okay, bummer. Oh, but it is in enough terms that we still can factor it out. VC will be G. I have L minus R minus mu kt, and I have a 2 and a square root. So, do you expect the velocity at C to stay the same and be the same as B, conceptually? Or do you expect the velocity as it goes up the loop to get less or to get higher? That is, I'm sure you've played with this when you were young. Yeah, thank you. So obviously we know that the velocity is going to get less as it goes from B to C and then less again at D. And eventually after D, if it stays on the ramp, then it should increase again. Sure enough, as you compare VB with VC, it's exactly the same, except the extra negative R. So, excellent point, Aaron. If the velocity is 0 at point D, can the object remain on the loop? Excellent. So it all depends how high the value of L is. In this particular problem, we want to make sure that the system stays on the ramp without falling out, which implies that the value of L, or H given to us, needs to be much, much bigger than R. If the value of L, initial potential energy, is too little, then as you try to solve, say, for the value of velocity at D, if you end up with a complex number right here, then it means that this term L is not big enough to fight the other negative terms. That would suggest that L was too small. Therefore, if you end up with a complex velocity, that means that this point is never reached. Exactly. So if this is the case, the object may leave the ramp at any point. It could be at C, it could be at D, it could be at E. That's actually a very, very interesting problem. So if anybody would like to work out this problem, a new problem for extra credits before the next test, go for it. That is, if you would like to calculate the minimum value of big L with respect to R, such that the system remains on the loop, please go for it. Give me your solution and submit it before the next test. Okay, for 5 extra credit points on the next test. Again, I repeat, the question and the challenge is calculate the minimum value of L in terms of R. So obviously L will be proportional to R. L minimum such that it stays on the ramp. That is, it doesn't leave the ramp anywhere. If you'd like to work out this interesting problem before the next exam, please do so. Submit it to me anytime, on paper, whatever, for 5 extra credit points. All right. So we know now VC. We're going to use the exact same technique. Perfect. Go for it, Aaron. We're going to use the same technique to figure out the normal force. This time we are interested about C. Therefore, let's do a free diagram at C. Similarly, we have the weight. We now have also the normal force, but the normal force in this case, since we're inside the loop, gotta be towards the left. And since point C is exactly at the height R, the direction of this force N is obviously in exactly the same direction as the acceleration, the real part. Perfect. That means that we can pick one of our axes in that direction, which means that as we apply Newton's law, what did I do? Let's pick X right here. In the X direction, Then the only force in the x direction is obviously n. That's it. And this acceleration ax is what we call ar. Therefore, mvc squared over r is the normal force. As you compare the normal force at B and at A, obviously it's less. The extra work term, weight term, is not going to show up. So as we going to go up the ramp, not only the velocity will decrease, but the normal force will decrease as well. So as you substitute Vc over here, you're going to get n at point C is equal to m r 2 g l minus r minus mu k d. Okay? So it'll be a little less. Wait. Okay? What will be the difference at point D in the potential energy term? As you redo this last part on your own, what will be different with respect to the potential energy due to gravity at point D compared to point C? At point C, it was mgr. At point B, it was 0. What will it be at point D? As you redo this problem between A and D, for example. At B, the potential energy was 0. At C, it's R. What would it be at D? How high is it at D? Excellent. The additional difference at D is that N and mg will be in the same direction. Yep. Therefore, as you apply Newton's law, you're going to have N plus mg is equal to ma. Yep. If the normal force, excellent, Ray. That's going to be the condition that you will use to solve for that extra credit point. Yep. So first difference, as Aaron pointed out, as you're going to do Newton at point D, both N and mg will be in the same direction, which means now N is going to be equal to mvd squared over r minus mg, while before we had plus mg. And the second change is the potential energy due to gravity. If we keep the same datum at F, and we saw the potential energy due to gravity at point B was 0, at point C was R, what would it be at point D if we're dealing with a circle? Yeah, thank you, Tyson, 2R. That's going to be the second difference here. That's it. Everything else will be the same. And again, as Ray suggested earlier, you could decide to redo the last problem and investigate point D between A and D, or you could do it between F and D, or you could do it between B and D, or you could do it between C and D. Do them all. Then you will master this type of problem. So if you see one type of problem like this on a test, woohoo, piece of cake.